So far, we've been discussing Newton's second law in very abstract terms, but now let's think about what it actually means to apply it to real systems. And let's just start with a system of particles. Any one particle, Newtonian particle, that is an infinitesimal point mass in space, has 3 degrees of freedom. We can think about these as the linear degrees of freedom. So it can translate in any one of 3 directions, like so. And then we can pick a certain set of coordinates to describe the motion of our particle. We can use Cartesian coordinates or polar coordinates or spherical coordinates or what have you. And if we take many particles, if we take a system of n particles, then each of these has 3 degrees of freedom in 3-dimensional space. And so the net number of degrees of freedom is 3n. If we further introduce constraints, like, for example, tying the particles rigidly together or imposing some other constraint upon them, then we lose the number of degrees of freedom as there are constraints. And so for k constraints, our system of n particles has 3n minus k constraints. And therefore, this system should be describable by 3n minus k coordinates, because at the end of the day, we want 3n minus k independent differential equations that give us the trajectory of the system, the position and velocity of each component part of the system. So we can go directly to a set of generalized coordinates and define q1, q2, q3, all the way to q3n minus k. These are known as generalized coordinates, and they are elements of the configuration space of the system. Now, we're used to thinking about Newton's second law as operating on the acceleration of each of these particles with respect to some coordinate origin O. And so typically what we will write is the position of each one of these particles with respect to O, but we can express this position in terms of our generalized coordinates. So for every particle J in our system, we can write an expression that is R J rel O as a function of Q1 to Q3n minus K. And that means that we can also define any set of coordinates, like let's say the Cartesian coordinates as xi, to also be xi as a function of q1 to q3n minus k. And so if we think about the differential, the total derivative of dxi, well, that's going to be the summation from some dummy variable that we'll call L, 1 to 3n minus k, the partial of the xi coordinate, and the with respect to each of our generalized coordinates. So this is q sub L times the total derivative of ql plus the, of course, the partial of the ith coordinate in time times dt. So just to make clear what the distinction is here, these xi's, these are the coordinates that I would get if I was expressing, for example, rj rel o in terms of Cartesian coordinates. So if I was doing something like with respect to the inertial frame, x1, x2, x3, and doing the same thing for every other one of the positions of every other particle in my system. So that is these coordinates, and they are different from the generalized coordinates potentially because these do not encode constraints, whereas the generalized coordinates are also automatically encoding the constraints. They are the minimal coordinate set of my system. One way to think about this would be in the case of everybody's favorite toy problem, the simple pendulum. This only has a single degree of freedom because this distance is fixed. It has a fixed distance L. And so if I describe this, the position of the pendulum mass in terms of Cartesian coordinates, I would have 2 coordinates. But in fact, we know that we only need a single angle coordinate to describe this position. So xy are overdetermined, and theta is critically determined, and theta can be treated directly as a generalized coordinate. Whereas for xy, we would need to write a trigonometric function to get theta. Back to our setup. So we can express every one of our, say, Cartesian coordinates or any other kind of coordinates as a function of the generalized coordinate set. We can take the derivative. And the reason why we are doing this is because we want to get directly to a set of differential equations in terms of our generalized coordinates. If you can set up your system in terms of the generalized coordinates and apply Newton's second law, then you can get there that way. But another path is via what are called the Euler-Lagrange equations. And the Euler-Lagrange equations are effectively equivalent to the application of Newton's second law, but you can get to them in a couple of different ways. And the way that we're going to look at right now is via something known as Hamilton's principle. So we're going to start by defining the Lagrangian of a system as the difference between the kinetic and potential energy of the system. So the Lagrangian L is defined as the kinetic energy minus the potential energy. And we are going to define the action of a system as the integral between times t1 and t2 of the Lagrangian. Hamilton's principle states that the motion of a system is a stationary point of the action. And what that means is that the variation in the action is zero. It is a critical point. It is a stationary point of the system. And so this is a basic idea from the calculus variations, and that is one of the methods that you can use in order to get to this result. Hamilton's principle and Newton's second law are encoding the same basic physics. We know this because we get the same basic result from them, but it is instructive to go from one to the other. And so in this case, we're going to start with Hamilton's principle and get to the Euler-Lagrange equations, which you see are a function of generalized coordinates. An important caveat here is that Hamilton's principle applies directly to what are known as monogenic systems. And that means that all non-constraint forces are derivable from a generalized scalar potential that is a function of the coordinates, the velocities, and the time of the system. So that's a monogenic system. So let's take a look. How do we get from this to this? The Lagrangian is a function of all of the generalized coordinates, their time derivatives, and time only. So I can state that the Lagrangian is going to be a function of q sub I dot, and time for I equal to 1, 3n minus k. That means that the action is going to be the integral from t1 to t2 of the Lagrangian. Now, let's think about any one of these generalized coordinates parameterized by some parameter alpha. And this is going to describe the path of the coordinate that's neighboring the true path. And so we will write this q sub I as a summation of qi t0, where this is the true path, plus alpha times an arbitrary function of time. Let's call this eta sub I. And the only restriction on eta sub I is that it vanishes, it goes to 0 at the endpoints of the trajectory at t1 and t2. So graphically, what we're talking about is a variation in the path. So we have a trajectory from t1 to t2. We have some true trajectory, and then we have neighboring trajectories. And so the true path is encoded by q sub I t with alpha equal to 0. And then all the neighboring ones are small deviations from the true trajectory. And the only restriction is that we end up where we need to go, and we start off from where we know we started from. In this case, the variation in I can be written as the partial in I with respect to alpha d alpha. And so we can write that is, we are taking the integral over the summation of all of the partials of the Lagrangian with respect to the generalized coordinates times the partial of the generalized coordinates with respect to alpha, the alpha, and the same thing with respect to the time derivatives of the generalized coordinates. We can take the second term and further rewrite this. So we're going to just focus on this bit, go over here, and rewrite this as taken the fact that qi dot is the time derivative of qi, and we've just pulled out that partial in time out of this term. That means that we can now put this back into the original expression, and we have something that we can integrate by parts. So integrating by parts, what we find is remember integration by parts, uv minus integral v du. But if you look at this, you have the partial of qi with respect to alpha from T1 to T2. And remember, our one restriction was that every single path has to pass through T1 and T2. And so this expression will vanish because the two things will be, the T1 and T2 terms will be equal to each other for all cases. And so this goes to 0. And so if we go all the way back to our expression for the first variation in I, we now have that is the variation in I is the integral from T1 to T2 of the summation of the partials of the Lagrangian with respect to each of our generalized coordinates minus the time derivative of the partial of the Lagrangian with respect to the time derivative of the generalized coordinates times the partials dqi d alpha evaluated at 0, because that is our center point, and then all over d alpha dt. And this term here, this we can represent as delta qi. So this is, we're defining this as delta qi. And this represents an infinitesimal departure of the varied path. Now, by the fundamental lemma of the calculus of variations, we require that in order for this whole expression to be 0, the coefficients of every one of these delta qi's has to individually go to 0. That is, we need every one of the terms in the summation to be identically 0. And so what we can get is 3n minus k separate expressions, one for each generalized coordinate, that says that the time derivative of the partial of the Lagrangian with respect to the time derivative of the generalized coordinate minus the partial of the Lagrangian with respect to the generalized coordinate itself must be 0 for all I 1 to 3n minus k. And this, finally, is what we call the Euler-Lagrange equations. And this is what is given here. So a few final notes. Hamilton's principle and Newton's second law are effectively equivalent postulates. Either one of them leads directly to these expressions, and we just saw how we get there from Hamilton's principle, and later on we will see how we get there from Newton's equations by way of D'Alembert's principle. The Lagrangian is a single scalar function of 3n minus k coordinates leading to 3nk differential equations of second order. Newton's second law provides up to 2 vector equations per particle via angular momentum balance and linear momentum balance, leading to 3n minus k differential equations of second order. And finally, let us never forget, even though this is all scalar equations, it is a function of the kinetic energy, which is a function of the velocity, which is a vector quantity that must be differentiated with respect to an inertial frame. And so no matter what you do, no matter what approach you take, you are not excused from thinking about whether a frame is inertial or non-inertial for your specific system.